Welcome to chapter 3.3, lesson number 2, where we're completing our VSEPR chart here and looking at what happens once we get to something with even more electrons. We've taken a look at beryllium, a common exception to the octet rule, boron, another common exception to the octet rule, in which we just don't have enough electrons to complete an octet, hence why we end up getting that particular set of exceptions. In this one, when we take a look at methane, all right, we do have 8 valence electrons available to us, 4 from carbon and 1 from each of the hydrogens, for a total of 4 more to give us 8. Carbon has the highest bonding capacity, so it of course goes in the center. And then we have to attach those 4 hydrogens to it, and each one of course takes 2 electrons to do so. And so we've used 8 to attach the 4 hydrogens. I have no more valence electrons left, so now I need to just double check and make sure that there's no correcting that needs to happen to my Lewis structure. And so 2, 4, 6, 8, that's all 8 electrons. Each hydrogen just needs its duet of 2, so it's satisfied. And when we take a look at the carbon here in the middle, you can see that it has 8. So everything is good. We now assess these particular pairs of electrons, and you can see that all 4 are bond pairs, no lone pairs, for a total of 4 pairs. When we have that arrangement, this is a 3-dimensional arrangement that we have, and so it does lead us into something that is known as tetrahedral. All right, and we do get that tetrahedral geometry as well, since every electron pair here is attached to a particular atom. The 2 shapes again are the same, like we've seen with the first 2 examples. So now we need to figure out how to draw this shape. And if you remember from the PhET website, all right, and again, I would look at some of these and make sure that you can build these particular shapes there. When we take a look at tetrahedral, remember it's greater than 90 degrees of separation. We start to encounter the fact that these are 3-dimensional shapes, all right, and we can spread out 4 pairs of electrons better than 90 degrees, as illustrated by Lewis, with a 3-dimensional shape called a tetrahedron. And we can get to just about 110 degrees of separation if we do this. And so the tetrahedron, when we draw this guy, is essentially 2 offset V shapes. We'll have one here that I can draw within the plane of the paper. So there's one V. And then I have another one that's offset, but this one would have to be out of the page and into the page, or using that depth dimension that we don't often illustrate on a piece of paper. So if one of those V's is within the plane of the page, then the other one has to be into and out of, all right, as we have some sort of depth here for that one. So how am I going to show something that would be, let's say, essentially sticking out of the page at us? Well, if you take a look at the textbook, what it's going to do, it's going to show this triangular shape in which the point at the carbon is shown small and the point closest to us for that hydrogen is shown large, trying to give us that illustration of something being closer to us with that line. And then of course we need that other V to be into that plane of the page, and so it kind of goes beyond the page. And so for that, just like drawing, like 3D cubes and stuff like that, we sometimes use dashed lines to show us what's behind a particular plane of the image. And so, as you see in the textbook, we use dashed lines for that. Okay, the purpose of these different lines for the covalent bonds is really just to show us depth into and out of the page, and everything we have here is that 109.5 degrees, or a greater separation than the 90 degrees that is kind of insinuated here. We have another one that we need to look at, and that's taking a look at ammonia. Ammonia has 5 valence electrons with its nitrogen plus 3 more with a total of my hydrogens. So again, we have 8 electrons available to build this. And so nitrogen with a bonding capacity of 3 would sit in the center. And in the center, we do have to attach 1, 2, 3 hydrogens, and I just arbitrarily picked those sides, didn't really matter. And so I've got 2 valence electrons left. Hydrogen doesn't need any because they're satisfied with a duet, so the only place they could go is here on that central atom. Now we need to assess these particular pairs, and you can see 1, 2, 3 are bond pairs. 1, however, is a lone pair for a total of 4 pairs. So when we take a look at the electron geometry, you can see that all 4 suborbitals in the octet are filled, which gives us that tetrahedral arrangement again. But when I take a look at the shape of the molecule, there's nothing attached to this pair up here. And I only have 1, 2, 3 attached atoms. All right, being that we're in a 3D tetrahedral arrangement, that is going to give us a 3-dimensional shape here called trigonal. Pyramidal. Okay, and so we essentially have a 3-dimensional triangular shape, and I would encourage you on the PhET applet there that you try this out and make sure that you can see this and recognize it. To draw it in a 3-dimensional shape, again, I need my nitrogen, and in our textbook, it does tend to preferentially show the same arrangement that we did for methane, in which you had 2 or one of those V's in the tetrahedral arrangement being within the plane of the page. One of them is a lone pair. The other one is one of your hydrogens. This leaves us the depth V, or the depth bent arrangement of the other 2 hydrogens for this structure. And so we would show something coming out of the page and something going into the page. All right, and so we still have that 109.5 degree separation from any 2 pairs of electrons. Okay, so there you go. You've got ammonium and you've got methane now explained, and we're starting to see a new occurrence appear that when I have lone pairs, the shapes are no longer the same. Okay, we'll continue these ones in lesson 3 and finish that off for you guys in the next video.